Oh, and we are live.
We are
Amazing.
live. Well,
Nice.
hello everyone. Thank you for being here. We're so excited to have Patrick with us. We're gonna be talking about how to write really good research code. Um, and this is one of the things that this is important after you have written hundreds and hundreds lines of code, and then think about, oh, there was a more efficient way to do this. So hopefully we learn how to do that. So Patrick was a super key player in making NMA happen last year, and you know that because this year I'm an organizer, and we find out, oh yeah, Patrick did that last year. Oh yeah, Patrick did that last year. Oh yeah, Patrick has that code. Yep. So Patrick was so important in making everything happen, and we're really thankful for him and also for taking time to do this today. So Patrick is gonna do his introduction and then go ahead and start. Patrick.
Awesome. Thank you very much. And so can you see my screen, my slides?
I'm gonna make them focus now.
Perfect.
Here we go.
Okay, so well, I'm glad to see so many people in large numbers. I was not expecting that at 10 a.m., but I'm not a morning person, so that's what I would expect. Okay, so yeah, who's this lecture for? I saw this thing on Twitter a little while ago, and it kind of like brought me like deep cringe. So this guy goes, "Is my code fast? No. Is it well documented? No. But does it work? Also no." So if you're kind of in that bucket, this is the perfect presentation for you. So most people who do coding heavy research are not trained in CS or software engineering. So you're probably in this bucket. I was in this bucket as a grad student. And as a consequence, you feel like you don't know what you're doing because you don't. And you might have imposter syndrome, and your productivity is low, and you have bugs in your code, and you hate your code so much that, when you meet up with other people outside of grad school, like that's the first thing that you tell them. Like, I've been trying to debug this code for the last 5 days and it doesn't work. And then you don't graduate and you have great sadness in your heart. So it doesn't have to be all that bad. So I kind of have like a weird perspective on this because I was once in the same kind of situation that you were. So I did my PhD in neuroscience at McGill, doing computational stuff. And then I kind of took a left turn and did the software interview and ended up as a software engineer at Google, where I was wildly underqualified. But I picked up some stuff, so that's good. And then I did some research science in brain-computer interfaces at our presenting sponsor, Facebook Reality Labs. And I helped build NMA as a CTO in the first year. So all these experiences like really helped me to like gain some understanding of software that I didn't have before, as when I was a grad student, and I feel like you might enjoy learning about my weird perspective. So I'm mostly self-taught. I really didn't study CS until like very, very late in my career. And I've wasted months working on bad code of my own making. So I think you might be curious about what I learned. Okay, so this is 2 hours. I'm going to take like about a 5-minute break in the middle because I have a very hungry cat that needs to be fed in the middle. It's going to be a very interactive kind of session. Don't be afraid to interrupt me or say a bunch of things in the chat. That's always appreciated. And some ground things. First of all, I'm going to assume you know a little bit about Python, about Git, and the command line. You can catch up on these topics via software carpentries. If you don't already know all this stuff, it's totally fine. This is a very like vertically integrated advice. So even if you don't totally get it, you can read up on the tutorials later and come back. And I'm organizing this talk around 5 practical tips to make better code with concrete examples. And you have 5-minute action items. So today, later in the day, you have actionable things to work on. So Yeah, so don't be afraid to interrupt me in chat. But first, I'm going to indulge in theory because this is one of the venues that I can actually indulge in theory and not be, having tomatoes thrown at me. Will the slides be uploaded somewhere? They are already on GitHub, so if somebody can find the GitHub link that I sent, I'm sure they can put it in the chat. Okay, so what does coding look like in the brain? So I'm just gonna test, whether you're all awake and listening. Perhaps some of you can chat and say, like, what do you think that coding looks like in the brain? Does it look like language, math? Does it look like vision? Does it look like, I don't know, like a sequence of motor actions? Like, what do you think it is? I'm just going to wait awkwardly until the chat comes up with a few answers.
We have a couple of answers in the chat.
Yeah, I can see. I'm waiting until I have a screen full. Okay, so I have a couple of answers that I see here. Okay, so making algorithms using math functions, like language processing. It spikes. That is factually correct, which is the best kind of correct, of course. Shaping the idea and structure. It's like math. So we have like a couple of one is a link to, I guess, like an article on programming in the brain. Awesome. Yeah. So let's look at some research. It turns out that the coding is very working memory intensive. So when I was looking at this, I figured, well, code probably has something a little bit to do with language, but that's not like really language. It's more like math. It's in a sense, right? And it turns out that there's some research from Fedorenko and others at MIT that looked into this. And so if you look at the loading of bold activity onto the brain, it turns out that there's a large amount of overlap between what happens when you're working on code and the multiple demand system, which is like this a network of areas which are involved in a variety of different tasks that are working memory intensive, that might involve math, for instance, any sort of complex planning. So it kind of looks more like a very working memory intensive problem than a language problem per se. So, as a consequence, you're going to get overloaded. It's just like something that like really, you have like these, let's say that you have like these 7 working memory slots. Like most of the time you're going to have like 6 of them full, and then you're just going to try to like move pointers around in order to defrag your memory enough so that you can put more stuff into your working memory. So I'm sure this has happened, like you're working on code and then you're typing and you're like, wait, what was I doing? So like that's the classical consequence of that. So we're going to try and conserve your working memory by reducing the cognitive load of your code. And this comes from the Zen of Python. Simple is better than complex, and complex is better than complicated. The other thing that I'd like to point out is that in addition to being working memory intensive, research code is also very long-term memory intensive, right? So you have like this nice process that you would want to use in theory in order to write a paper, but oftentimes it's more like a jumbled mess of like going back, creating the data, and then you figure out that it wasn't the right data in the first place. So you go back and you find some more paper, and then you fit the model, and then the model doesn't work. And then, so in order to understand like that one piece of software, oftentimes, you have to understand everything that that's happened before. You know, like you need to know about like this one grad student who was just there for 3 months and then like ended up starting a farm in upstate New York, because that's the one thing that's the one piece of information that you need to know in order to get this code to work. And so you have to remember all of these dead ends for the code to even make sense and even be runnable. So future you will have forgotten 90% of the code that you wrote. I'm sure this must have happened to you. Like you wrote a paper and then you get back the reviews. You haven't worked on the code for 3 months, and then you're like, you know, the reviewer is like, "Could you change this one figure?" And you're like, "No, I have no idea how to recreate this figure. That's horrible." Yeah, ideally it wouldn't be this way, but sometimes it is. So debugging is twice as hard as writing the code in the first place, and you have to remember all this stuff. So if you write the code as cleverly as possible, you're never going to be smart enough to debug it. So, you know, write kind of obvious looking code. Okay, so my thesis is that writing good research code boils down to two things: saving your memory of the working memory subtype and the long-term memory subtype. Cool. Okay, so are we all cool with this? Yes. Can we get some yes, some thumbs up in the chat before we start into the practical lessons? Okay, awesome.
Start coming in.
There's like a 10-second delay or something, right? Nice.
There might be, yeah, there might be a 10-second delay. Yep.
Awesome. Okay, so again, yet another disclaimer. It's okay to write garbage code if you're in a rush. If you don't do this, what I'm proposing, every single time you do a research project, it's fine. I understand, you know, sometimes you have deadlines, you have like all this like crushing pressure, and but like I just want you to graduate, you know, or to accomplish like whatever is the next, you know, goal that that you have in mind. I'm not like a very judgeful person. So these are guidelines, not rules. Okay, the first lesson is let's all channel Mary Kondo and let's keep things tidy. So what needs to be tidy? The project folder structure, code style, notebooks, scripts, and if you're going to do this, you're definitely going to mess up a lot. And as a consequence, you're going to need a time machine. And what do we use for a time machine? Git and GitHub, right? So that's our record of everything that we've done. So I think there's a general consensus in the research software engineering community that one repo should equal one project, which should be about like one paper worth of research. There's a lot of templates going around for this. I'm going to use, I think, one of the simplest one, which is called Schablone, which was cooked up by Ariel Rokem at the University of Washington. I like it because it's super simple and it shows the basic nuts and bolts. But once you've implemented something like that, you know, you can branch out and try something else after that. So the way it works is that you know, Schablone is organized along along a standard template. So of course there's a README file. Then you have the core code, which is inside of a folder, which is named the same as your project. So because the project is called Schablone, the folder is called Schablone. Documentation is set up in its own separate folder. The whole thing is Python packageable, so you can pip install it. I'll get to that again later. And then you have an extra an extra folder for scripts, right? So every time that you see a project which is organized along these lines, it's not like really hard to figure out where the stuff is. You know, it's like nice and organized. So it's pretty lightweight. The thing that you can, the feature that I think is the strongest, or is like the most important, is that it's compatible with Python packaging. So that means that you can install it locally using pip install -e dot. and then the code inside of the special folder becomes part of the package that is installable. So I think that that's a big obstacle when you're doing Python. I remember, like, I started in Matlab, I'm sorry to say. And in Matlab, if you wanted to include code, you had this notion of a path, right? And the path was easily accessible through a GUI, and then you would get to poke around and add like this these M files to your path. In Python, it's not as obvious. You know, they've kind of hidden the functionality behind pip. So this kind of setup allows you to, you know, get back to kind of that workflow where you can add things to your path and then use them from several different locations. So I'll go in a second through actually doing this. Okay, live demo, perfect. So, oops. All right, so let's open Firefox. Sorry, I'm just gonna make sure that both of my windows are open. Schablone, arrow. No. There you go. Okay, so this is the repo. This is normal GitHub, except that I have it set to the dark theme, so the background is black. If you're not used to seeing this, so the way this works is you just click this big green button, use this template, and basically you can use it. You can duplicate this template and making your own. So Schablone dupe my Thesis project. By the way, if you find my screen hard to read, just let me know, and I will Control+ to make the text bigger. So what we've done here is.
Hey Patrick, it is a little small.
Yeah, got you covered.
Yeah, that's better.
Awesome.
Yep.
So okay, so now I have this this project folder inside of my GitHub, and it's generated from this original thing. So it's kind of like a fork, except it doesn't like really have a link to the original thing. So it's my own. So that means that I can take this code. If I want to. Oh, this is not the right one. This is the right one. Okay. Oh, I've done this several times before. So I already had a folder that was that. Okay, so I'm just going to git clone this thing so you see what's going on here. I'm going to go into an environment. I think I have like just want a clean environment that, I called it RC. There's a little bit of cooking show magic because I did stuff before to prepare. So I had created an environment in Conda, which is called RC for research code, and that environment is empty. So which means that if I type Python here, you can see there's Python 3.8. Oh, control. I think I can also make this larger. Yes. This is going to be much better. Better at home? Nice. Okay. So if I import Schablone now, okay, nothing happens as is expected. You know, there's no such package at Schablone. Yeah.
One little thing, because our faces might be covering the bottom of the terminal.
Can
you like scroll the terminal?
So I just scroll up. Yeah. Perfect.
Yeah, I think that. Yeah.
Okay. So
maybe even move it to the right screen just to like just to be sure. To the right part, yeah. Perfect.
So right is better. Cool. So yeah, so Schablone doesn't exist yet, but now if I do ls, I can pip install Schablone. So How's that work? That. And then it's just going to install it. Right? It's going to install it with the pip dependencies as though it's some like magical package that I got off of PyPy. It's as easy to install as something like Seaborn or SciPy or whatever. And then that means that wherever I am, if I call up Python, I can now, sorry, I'm just going to get used to scrolling. I can now import Schablone. Except that this time, do credit didn't work. That's okay. I'll just install do credit. Sorry about that. It has like this one dependency. I think I asked Ariel to fix it, but okay. Let's try this again to show I wasn't lying. Import Schablone should work. Yes, it's worked. So now I actually have access to all the code that was inside of the Schablone folder. So that code, let me show you what kind of code it is. So for instance, there's this code that I now have access to. And so this code is example code in order to fit a function that you can peruse at your own leisure. But the point is that now I have access to it. It's a library that I can use from anywhere. So this is nice because like once you have a package set up like that, you can reuse code across different projects. So this has probably happened to you that you have like a special library of code that you're carrying from analysis to analysis. Like one thing that I have is a library to fit Gaussians, right? Because you're always fitting Gaussians. It's kind of a pain to actually like figure out what the parameters are. So then I can use it. I can reuse that across a bunch of different projects. So I'm going to read some questions now. Now that the demo is mostly done. Can you also hide the screen sharing banner, please? Yes, absolutely. What does -e mean in pip install? So you may be more familiar with, let's say, pip install Seaborn, right? So where you have the name of a package. When you do dot means the current folder, right? So pip install dot means the current folder. But in order for that to work, you need the -e flag. I'm not actually sure what the -e flag does. I just use it.
I think it's development mode.
Oh, -e is development mode? That makes sense.
Yeah.
So that's kind of a technical distinction that's a little bit hard to explain. But basically, when you're in development mode, that means that Python doesn't like create a copy of the package that you're installing. Instead, it creates links to the package that you're installing. So if you're developing that package and you make changes to it, the changes will propagate across all the projects that use this package. Why are we using pip instead of a conda environment? Shouldn't we use conda install? So packaging in Python is kind of this funny thing, right? Where conda kind of has like this very like kind of large scale environments, and then oftentimes pip has kind of like smaller scale environments. So I use conda like other people's conda environments, but I rarely create them. And so for this kind of project, I think that pip is kind of the right target, and it works with setup tools in Python. Yes, but yeah, you can use pip inside of conda. It's not a problem. In fact, you should use it instead of using pip in your base environment, which means that it's going to be like a nightmare to figure out what's actually in your base environment. Okay, so lots of questions about conda and pip. I hope that this is a little bit clear. You can also ask a question. Let's look at the ask a question. Assuming you develop, when do you use relative imports versus absolute imports? Does this matter for sharing your project with others? Yes, it does. It does matter, and for relative imports versus absolute imports. But I think that we're getting maybe a little bit in the weeds. So I think if we run into it later, I think I'll come back to this. Pip versus Conda if you're creating a new environment for ML Neuro project. Yeah, so what I like to do is, so here's my, I'll just show you this once, because I realize now that I've kind of opened the Pandora's box of Conda versus Pip. So this is my 100% everyday recipe for creating a new project. So first of all, I create a new project, -- name, in Conda. I always use Python 3.8, and unless I have like a very good reason not to. And I activate this this new environment, and then inside of it, I pip install stuff. So maybe I want to. So once I've activated this the first time around, example. Then I can pip install whatever I want, like let's say Seaborn. So that's my, yeah, so Zara is asking about the headaches that are involved with different Python versions on the system, each with their own package installations and import. And I think that just use Python 3.8 for now until like Python 3.9 becomes the new stable version. That would be like, unless you have like a very good reason to use some like old version of Python. Some packages do require older versions or something like that. Okay, so I'm going to move on in the interest of time. So. Right. So where are my slides? There we go. Okay, so whatever template that you use, just make sure it installs this local package. So stuff that we saw with pip install -e. I have this long form notes on how packages really work. I have a feeling that with this audience, you're very, very curious about this. So if you click on the slides, if you go to the slides, there is one of these things is actually a link. And then you can read the long form note with all the explanations. It's kind of technical and annoying. Okay, other conventions that I like. Notebooks, I like to start them with a capital letter and with spaces. For reusable functions and packages, use snake case, that's the Python standard, and then tests under the test folder. You might not know what a test is right now, but we'll get back to that in section 3. To organize scripts rather than notebooks and the rest. I like this suggestion from a paper from Van Vliet from 2020 that essentially does, if it's a multi-step pipeline, basically he creates scripts which are named against the step in the process. So if it's the first step, it's called 00 fetch data.py. This particular scheme doesn't quite work because then you can't import the code because you're starting with a 0 characters. So I would just say, just start with step _ whatever if you want to use this this convention. So instead of doing like 00 fetch data, call it step _ 00 fetch data. And then if somebody comes in and they're like trying to figure out what's going on with the code that you're using, then they can see where in the steps they are. Like they can figure out just by eyesight what the main steps are and what the relative progression of things are. And then you can make a master script that binds everything together. Recently, I started using make to do this, which is super fun. It's like this ancient like wisdom kind of thing. But there's newer tools like Do It and that are pure Python. Yes. Okay. Code style. So just so you know, I'm going to continue with the presentation until I get to the end of this section, and then I'll answer some more questions. Use a consistent style. So Python has a style guide, which is PEP8. So it tells you things like how do you indent stuff, what's the line length, spaces, variable names, imports. And a place like Google has their own like super pedantic style guide. So like that's, step one when you join in. They're like, oh no, you can't like put this code in the main repo because, it uses, I don't know, like 2 spaces versus 4 spaces, or maybe it's the inverse. Yeah, it's very pedantic. It was even to the point where Guido van Rossum, who's the inventor of Python, when he did join Google, he had to go through a process to learn Python at Google to get him readability, even though he's the one who made the thing. But basically, so that means that whatever code that you write, I mean, it's not even clear who writes the code anymore. It's just in a standard kind of format, and it's not like very hard to read because it always kind of looks the same. So there are linters and auto formatters which will get you your code in this format, and you can install them in VS Code. So if you haven't used VS Code, we'll see it come up later. You'll see me code inside of VS Code. If you like it, you can install it, and it's just a nice modern text editor that has all the accoutrements that you expect, like plugins and so forth. Doc strings, so doc strings are basically your documentation for your functions. There's a standard format that you can use for this. This is more useful if you write code for others or for yourself in the future, which is probably true. That's probably the case. I think IPython notebooks are a really nice way to shoot yourself in the foot. I love IPython notebooks. I love them, but they're breaking my heart. So notebooks are hard to keep tidy because of the nonlinear execution. So as I'm sure you've run into during Neuromatch Academy, you have this issue sometimes that you run a cell before another one in the inverse order they're supposed to, and then it just like kind of crashes and burns. If your notebook doesn't run top to bottom, then it's not easily reproducible. So my suggestion is to try and like titrate yourself away from IPython notebooks as you become more comfortable with doing Python coding. And you can do that by taking the code that you put inside of notebooks and then package it up using, for instance, Schablone. And then you can easily auto-reload your package code to make development easier. So there's a special incantation you can use in IPython notebooks that auto reloads the code if you change it. And it works pretty well. Okay, why does all this matter? Well, you don't have to constantly ask yourself like where the stuff is, how you should do thing X, and basically you're liberating like a couple of different working memory slots to focus on the stuff that actually matters. So I've been through this like pretty in like a pretty extreme fashion. So basically at day 3, when I joined Google, first of all, they give you the funny hat with the propeller, and they set you on the bike, and you play your Quidditch session and so on and so forth. But then on day 3, you actually have to program, so it was time to do a code. And they just like throw you into the one giant mono repo which has billions of lines of code. And it seems horrifying. But everything is organized according to strict conventions. So it's really not that bad to jump in. It's okay. You can figure it out. All right, so lesson 1 is keep things tidy, free your working and long-term memory from having to remember where stuff is. And the 5-minute exercise is going to be to use the Schablone template for a project. So now I'm going to go ahead and take some questions before we continue. Okay, so I have, so there's more questions about Conda. I think I'm not going to answer more questions about Conda. just because that's I think it could be like a kind of a long discussion, but maybe I should write a blog post about conda versus pip. Maybe that's the solution there. Svikroot says Spider is nice for projects. I actually like Spider too, in addition to VS Code. There's a bunch of different IDEs. I've rated them actually on my blog. I've tried all of them, but I ended up using VS Code. Then there's IPython notebooks. Oh yeah, so so it's funny because there's kind of two extremes on the IPython notebook. And some people really, really like them and use them for everything. So most notably, Netflix does all of their data science and their machine learning pipelines inside of IPython notebooks. They don't use like regular Python for that, which seems, I mean, that's like that to me is kind of like a non-starter for myself, but that's just my personal opinion. Other people are more on my side, where like I try to use it just for plots and data analysis stuff. Nice. So people are actively involved. Let me look at the polls now. Pandora's box. Okay, good. All right. So I think we're ready to move on.
We do have a couple questions on the ask a question at the bottom there.
If you're trying to take a TDD approach, so that's from Sophia. We are going to talk about that in the third hint. What do I think about more advanced workflow managers instead of Make? I like Make. Make is cool. I haven't tried many others, but some people swear by them. I didn't have time to try all of them. Sorry. What do you do for managing dependencies? Theses are always conflicting and out of date when developing in Python. Yeah, definitely. Some combination of conda and requirements.txt. And also I've started using Docker to, if something like I really want to preserve for humanity for the next 10 years, I'll use a Docker file, since those tend to be a little bit, they tend to have kind of a longer shelf life. And then we have a couple of questions about pips. I think that we're ready to move on to section 2. Yes. Okay, so lesson 2 is to keep things decoupled. I love this figure because it's so old, and it's old, but it's also like old school. Love it. So have you heard of spaghetti code? Maybe Alex, you can answer, because this is it's going to be.
Well, I get the gist of what it means. All over the place, no?
So spaghetti code, and I want to be very clear to the people at home that may enjoy pasta, which I'm definitely like one of those people that is, I'm very carb friendly. And this is not like al dente spaghetti. Like this is like the worst kind that just like kind of comes off, and basically you take like one strand and just the whole thing, like the whole blob of spaghetti like comes with it. So that's a kind of a development anti-pattern, right? So it's just code that is unstructured in a way that is very hard to reason about. And so maybe your code is written in a way where you're doing a little bit of everything all at once. So I tried to find some code, a code example, but it was hard to find like a good code example without trying to be mean. So I'm just going to pick something that I actually used for a long time during my PhD, which is WaveClass. So it's a really useful piece of software in order to sort spikes. If you have like a Utah array, for instance, you can use that. And I picked it because it's real code. So if I look at this particular example, I think that here's the link. So it's a function that I looked at. So it's a function that's inside of the GUI of wave class. So it's a callback, right? So what this particular function does is okay. So there's a couple of things that are like kind of code smells in this code. So first of all, you see like lots of changes from like one type to another. Like you have like string to double, and then eventually you'll do like a double to string. So you're passing like data like not in their original formats. You have things like using eval. That's a big code smell. You have like lots of magical numbers, right? So like, in the 16th cell, there's some piece of information that relates to the GUI. In the 15th cell, there's some other piece of information. And then, it mixes this like very simple computation that it does, or like very simple bookkeeping with things like plotting and loading images, right? So it's like kind of does everything at once. It's actually really hard to reason. And you might think like, oh, the problem is that there's no comments in this code. So how could you possibly know what it does? But I don't agree. I don't agree that that's the problem here. The problem is more like a fundamental thing where it tries to do like a bunch of different things in this order. And for a lot of everyday code, the comments like don't matter as much as kind of the logical organization. So okay, so what's going on here? It's not complex, but it's complicated, I guess is what I'm trying to say, right? So code which does a lot of unrelated things at once, it becomes very hard to reason about. So if your results are weird, if you do an analysis and just, I'm sure this must have happened to you, like, you have like some plot of data that you have and, you go to your advisor and you're like, I don't understand what this means. And they're like, that can't possibly be right. I mean, that's clearly, it's not even wrong. It's just weird. There's some bug in your code, like go back and come see me in a week. So if your results are weird, it could be weird because the data is bad. It could be weird because, you're loading the data wrong, or your model is incorrectly implemented, or maybe your model is inappropriate for the data, or maybe your statistical tests are inappropriate for data distribution. There's just like a lot of different pieces that could go wrong in the process of producing a solution. So the solution is to kind of like package up all these different things, make sure that each of the boxes is like nice and tightly decoupled to each of the other ones, test each one to make sure it actually works. And then, by assumption, if each of the boxes individually works, then all the boxes together should play nicely. That's the theory. So we're going to do a kind of a separation of concern. We're going to keep each of the boxes small. So we won't make giant monolithic functions. So no 300-line function that does a lot of things. My go-to here is to say that just keep the function so that it fits on one screen. And which is very subjective because, you could be using a giant, 30-inch monitor, or you could be using like a 13-inch laptop. It still works, trust me. And the other thing that I would say is to avoid side effects. So this is kind of a computer science term that you might not have heard, or like pure functions. What is that? So a side effect is basically when you have a function and the data flow is not the most direct data flow. So the most direct data flow, basically you're thinking like a waterfall. So your function, your def function, it takes in 1 argument, 2 arguments, 3 arguments, and it processes this data, and then it returns some value that's computed from these arguments. And so all of the flow goes from the arguments to the return. But oftentimes in Python and in other languages of the ilk, there's also side effects, right? So you go inside the function, but the function may change data that's outside of the flow of the function that's not listed in the arguments or the returns. So maybe they modify a global variable, or maybe it modifies a static local variable, or a reference to the original variable, or modifies a mutable argument, or maybe it does I/O, right? So input, output, and or like it writes to a file or something. And that is like really, really hard to reason about. So if you can avoid it, create some functions that don't have side effects. So that's like so maybe you've heard of functional programming. So in functional programming, like nothing has a side effect. I'm making it a little bit simpler than it actually is, but that's the idea. So let me give you a specific example. Okay, so this is kind of like a little mini test and to make sure that we're all awake. So the question is, what will be printed by this code? So it's a function which is called Reversey. The idea of this function is that it should reverse its arguments, right? And it looks like this. So what will be printed by this function?
Feel free to answer on the chat.
Yeah, feel free to answer in the chat. Or maybe someone can look at the next slide and then tell me what the answer is. If you're already on GitHub. Yeah, so it will. So the answer, the only tricky thing about this thing is it's not the logic of the function. The function is, does the thing that it's supposed to do, which is reverse the arguments, right? Which seems pretty clear. So if you're wondering, like, what is this line? Basically, it takes the stuff at the start and then exchanges it for the stuff at the end, and then it keeps doing that. So basically it switches this and this, and then this and this, and then this and this, right? And as a consequence, it reverses the array. The problem is that array here, because array is a list, this not only changes the list, the output list, right, which is list B, which says 210, but also changes A, right? It changes the original list. In fact, there is no two lists here. There's just one list because of the mechanics of how references work in Python. So that is a function which changes its own argument. It mutates it. And as Akshay says, Python lists are passed by reference and are mutable, which seems like a lot of jargon, but yeah, it doesn't create a copy. It just like acts on the list itself. So the solution here, so Python has like this nice convention, which is that in the base library, if something mutates something, it will not return the same argument, right? So an example that you might be familiar with is sort versus sorted. So sort sorts a list, and it sorts it in place, right? So sort of a list returns nothing, right? It returns none because actually it changes the stuff that you put inside of its arguments. Whereas sorted actually creates a copy, so it doesn't mutate its argument, and so has a return. So that's one way that you can tell in the base library whether something mutates or not. But I think a convention here, which is if you're going to change the arguments, like don't return them, because that's really confusing. That kind of breaks the mental model of the user, is generally a good one. So side effects are not the best. Okay, so I think I'm gonna skip this because I want to move a little bit further to section 3, and we're gonna implement fib.py a little bit later in a test-driven development. Okay, so sometimes you're gonna come up with bad ways of interacting with your language because you don't really know the language that well. So I think that half of the people here said that they're from a Matlab background, right? I saw in the polls. Oh, it's gone. But there used to be a poll that that said that about half are coming from Matlab. So
it's a third, about a third we have.
Huh?
We have a third Python, a third Matlab, and a third other. Basically.
Okay. Cool.
Yeah.
So one thing that that you might do if you're coming from Matlab, for instance, is to use raw NumPy arrays like everywhere, rather than use the name column in pandas, right? To use data frames, because you don't really know pandas that well. And pandas is I mean, it's, you can't like pick up pandas in a half hour. It's definitely like you at least need to spend a weekend to like get to know the basics. But you know, here's a normal paradigm in Matlab, which is referring to like the 8th column or the 9th column and not having it a special name. But if you use that in Python, you're going to shoot yourself in the foot, because it's very easy to be off by one column. Using unnamed dimensions in NumPy rather than xarray. So that's if you use like big tensors. Using like bespoke casting for string formatting instead of using the one true solution, which is the F string, which is wonderful, which we all love. So you know, you can take time to learn more about the language that you use, and that's going to come over time. And also, if you read other people's code, oftentimes you can find better, more idiomatic ways of expressing what you're doing. So I'll encourage you to join open source projects or to read other people's code to figure out what they do, because you can always learn something from looking at other people's code. I think that recently I learned that there's it's possible to like get an item inside of a dict, but if it doesn't exist, then instead of returning an error, you can return a default value, which I was like, oh man, that's so much better than using try except. And I saw it in somebody else's code. So that's always helpful. Now, if you're coming from Matlab specifically, I do have 3 tutorials that I put together, which are linked in the slide. And people have said that it helped them, you know, with the transition. So, you know, just take it if you want. Okay, so I want to show you a specific example of, you know, decoupling and what it looks like in theory. So, and I wanted to kind of cook up an example that wasn't too contrived. Which is always hard, right? So I'm going to show you CKA. So CKA is centered kernel alignment. So the question, like the underlying research question, let's start with that, right? Is how can you compare different brain areas in artificial neural networks? How can you compare their representations? So, you know, a lot of the research in the literature says, well, you choose a standard battery of stimuli, you measure the responses across systems, and then you compare the responses between the systems, right? And there's many different approaches, like forward encoding models, and you might use canonical correlation analysis or maybe representation similarity analysis. But the one I want to focus on today is this particular one, CKA. The reason I want to do CKA is the bottom part, right? So it's not implemented in SciPy or sklearn, and GitHub gives very few hits. So it's like real research code. That being said, there is, if you're wondering, like, oh my God, is there really no code for this? There is. It's somewhere in an IPython notebook, and it's pretty well documented. But the point is that, like, this is the kind of situation, like if you read a paper and you look at like a really cool method, and then you're like, oh my God, like can I get it? Can I get this to work? That's like that feeling of like, oh, like now we're really in research territory. That's the feeling I want you to, familiarize yourself with. Like this little feeling of discomfort is kind of like a good place to be, because that's where the innovation is. So let me tell you some facts that we know about CKA, just so you know, like a little bit how it works. If you're familiar with correlation coefficient, think of CKA like a correlation coefficient, but instead of between two vectors, it's like between two matrices, right? It's actually like kind of the square of that correlation coefficient. There's a particular formula for doing all this that I'm not going to go into, but the point is that the minimum is between 0. It goes between 0 and 1. Like it's kind of the square of a correlation coefficient. And if x and y are one-dimensional, then the CK is just the square of the correlation coefficient. Again, that's a lot of background. Just I wanted to create like a real problem. So maybe I didn't hit the mark here, but let's look at some not ideal code to see like how we could fix up code that actually implements CKA. So, all right, so it's called CKA not great.py. So this version is not great because I wrote it this way. Okay, so I'm just going to, I am going to show, okay, I'm going to show this part. Right, sorry, my screen is not that big, and there's a lot of things to look at. But this is the basics of it. So I'll just do a little bit of a follow through to explain to you what's going on here. But basically, I load some data matrices through using Pickle, and then this is the special sauce that makes CK happen. If you look at the equations, you're like, oh, that kind of reminds me of correlation coefficient. Yep, it's pretty similar to a correlation coefficient, but with other stuff going on. And then I store it somewhere, and then I do some plotting here. So I am going to say to you that the implementation is fine. It actually does work. It's not broken or anything. That's not this is not the point. What I want to showcase instead is like, what do you think could be made better about the way that this code is organized? So I'm going to take some answers from the chat, if you will.
And just to be clear, Patrick, you just want comments on like the structure of the code, or comments, or like.
Yeah. A little bit of everything. So Moritz just said, create functions to modularize code. That's a great example of one action that we could take. Then we have and Elena said, not hard coding the range. So here I do hard code the range. That is indeed like a bit of a code smell that, one day this could very easily bite us, because suddenly we're not comparing, 5 matrices, but now we're comparing 6 matrices, and then it doesn't work anymore. Maybe it needs vectorization. So vectorization is kind of so when I was in grad school and I took a computational neuroscience class, people always said, you have to vectorize everything because, we were using Matlab, and that was like really the name of the game. And vectorization can often make code more terse, and it can make it much faster, especially if you don't have a JIT or a just-in-time compiler. But sometimes it can make code way harder to read. So I actually like don't they say that premature optimization is the root of all evil in computer science. And I kind of abide by that. So we're not going to vectorize it more here, because I think you could try to vectorize it, but then it would probably make the code harder to read. And right now, performance is not an issue yet. Too many for loops. Yeah, I guess so. Yeah, I guess that's true. Document is unclear to an outsider except equation 4. Yes. Sorry, you can't see the documentation. Actually, like this is important. If you implement a method that's in a paper, like put a link to the paper in the documentation, because you're totally going to forget where you got this code from or got this idea from 3 months from now. So make sure to do that. You could extract some quantity instead of separate variables, instead of doing it all in line. Yep, that's good. Xticks and Yticks is hard coded also. So this kind of code, this like very explicit code for what's inside of each matrix, I think is it's not ideal the way that it is, but sometimes you have to write this very explicit code in order to do figures. And you're better off to do it at the Python level than to try and mess around with your legends. And in Illustrator, I did this all of grad school. It was a terrible idea. Don't do that. This returns an upper triangle matrix of values, right? Yep, it totally does. And there's some trickery here. So this is an example of me trying to be super clever. So so what happens is I calculate the upper triangle part of a matrix, and then I take plus the transpose of that in order to fill the other half of the matrix, and then I add the identity matrix on the diagonal in this line of code. I mean, this is like an example of vectorization, so it's very efficient code, but it's kind of hard to read if you don't know what's going on there. So that's kind of a counter example. But I really like what Tong Liang said, which is separate plotting and calculation. That is exactly what I was trying to get to with this code, is that like everything's kind of done all at once, right? So first of all, there's so we have the matrix opening and the loading, and then we have the calculation, which is what we care about, and then there's the plotting. Right. So the fact that all of these things are all done and they're all inside of actually like the global namespace, that might kick us in a little bit later. So we're going to use some cooking show magic here in order to show a different example, which is a little bit better, which is the step 2 version. So what I did here is pretty straightforward. Basically, I took this and then I extracted it to be its own thing. Right. So this middle part, which does the calculation, I just extracted it into its own function. So now I'm calling this multi-CK because it does this on multiple matrices, and so these are the representation. It's a list of NumPy arrays. If you're not used to seeing this this kind of annotation, this is type hints for Python. So basically, you're just like trying to explain what is the type of the different arguments. So this function takes a list of NumPy arrays and returns a NumPy array. This doesn't actually like do anything. The hints are just there for documentation. They're not there to, tell Python the types of data. At least not now. One day Python will be typed, maybe. Okay. So what I did is basically I took all of the code that was in CK Not Great, and I just put it, all the numeric code, and I just put it in one function. And then what I did is I put the core code that I had. So the logic, right, which is loading the code, doing the CKA, and then doing the heat map, I did that in the main function. And then I use this funny thing, which is if underscore name is equal to main. So maybe we can start with this question. Why should we put so okay, so I think that putting the numeric code inside of its own function makes a lot of sense, right? And I'll show you later that once you do that, then it's a lot easier to test the code. But why put the rest of the code inside of a main function instead of just putting it in the global namespace? Maybe somebody can answer that or speculate. So Marit says, if you import the script, it will run automatically. Yes, that is a concern. We're doing a little bit of foreshadowing here because eventually we'll want to test this stuff. And the way that you test stuff is you write a script and you import the thing that you want to test. So if on import it actually runs all this other stuff, then it's going to take forever to run, and also it's going to generate plots, which is not what you want. You just want to test the numeric code. So that's one reason. Order of running strip. Okay, easier to import. Yes. So Arini, that precisely, it is easier to import it in another Python file. And then Arslan says another very good point, which is it will clean the namespace after execution. So this is something that I think is kind of tricky about Python, which is the way that globals work. So if you don't place this inside of main, all of these different, like the C here, DF, AX, all of these will now be globals. And that means that when you call multi-CKA, there can be, if the variable doesn't exist, the function will try to find it in the global namespace. And that can make for really, really gnarly bugs. And I don't know how many times that I had bugs that I couldn't figure out. And it turned out that it was this really stupid thing. And it really shouldn't be in the language, but it's too late now. It's the language is 30 years old, so what are you going to do, right? So it's a design flaw. So the way to get around that is to put all the code inside of a function. And now I know that some of you that are not used to this style of code are going to say but how do I check if my code is good? Now I can't really comment out stuff and see what happens. I can't look at variables at the end to see if the variables are correct, right? So we're going to fix that in section 3. We're going to introduce test-driven development, and that's going to give us new superpowers. I think that's pretty much all of my presentation too. I'm going to guess. Yes. Live coding, decoupling, configuration. Okay, there's more stuff. You can read this on your own. But so I hope that this was instructive. We're going to take a 5-minute break. Alex, if you can put me off the camera because I do need to feed the cat.
Yep.
And I'll see you at 11:15 my time, or I guess 8:15 your time.
Yeah.
All right. Awesome. Thank you.
We'll be back in 5 minutes. Patrick is just going to go feed his cat. But if you have questions of that previous part, just make sure to put them in Ask a Question. And let us know what questions you have about structuring your code so far.
Am I back?
You are back.
All right. That was quick. I'm happy to report that a cat called Quest is fed, and she's very happy. She was, you couldn't hear her, but she was crying the entire time. Like the last half hour, she was like, torture, torture.
Good timing.
Yeah, it's good timing. Nice. Okay, so I hope that that all of you are back and awake and happy. This section is going to be, I think, pretty beefy, and I think for many of you that come maybe more from a neuroscience as opposed to an engineering background, it's going to be some new material, which is this idea of building around testing. So I'm going to read this. Most scientists who write software constantly test their code. So you make sure that you've tried to see how well the code works by running every new function you write. You look at the inputs and the outputs of the function to see if the code runs properly without error, and you see whether the results make sense. So automated code testing takes this informal practice, makes it formal, and then automates it so that you can make sure that your code does what it is supposed to do, even as you go about making changes around it. So that's Ariel Rokem from University of Washington. And I think that, that pretty well sums it up. I could have written my own version of this, but it's about as good as it gets. It is really what it's all about. So it's formalizing this informal practice that you have. So let's consider a function, which is fib.py. So fib.py is going to calculate something that I think many of you will be familiar with, which is the Fibonacci sequence, right? So the Fibonacci sequence goes that an element is equal to the sum of its two predecessor elements, and the sequence starts with 1 and 1. So it goes 1, 1, 2, 3, 5, 8, 13, 21, and so on and so forth. So I am going to, let's try coding up a quick version. So I have a function here that does the Fibonacci sequence, but I think that we're a little bit ahead of time. So I'm going to do a live version, right? So our goal here is going to create a function which calculates the Fibonacci sequence, and then fib of n is defined as fib of n minus 1 plus fib of n minus 2. And we're going to find the 0th as 1 and the first one as 1. Okay, so if we want to write this code, we have the definition that's right in front of us. We can code this up recursively, and peer programming with 200 people, no pressure. Yep, totally. Actually, last time that I did this, I messed it up and I introduced an error. One on purpose and one not on purpose. But because I already had a problem on purpose, it felt a little bit better. Because it was like, no, I did this on purpose just to show you the magic of testing. Okay, so if n is equal to 0, return 1. If n is equal to 1, it's not great code, but whatever. And then else, return fib n minus 1. It's fib n minus 2. Okay, that's it. That's it. That's the whole function. This is not a good implementation. I can hear people just like screaming on their insides. They're like, but this is like recursive. You're going to your stack is going to be so big and you have so much. That doesn't matter right now. We're going to deal with this later. So if we wanted to test that this gives us the correct values, how would we do so? How would we do so? Alex, I think yeah, it might be good to do this because there's going to be like lots of little back and forth. So
Okay. I'll be
yeah.
here. I don't know, create an to test it.
Mm-hmm.
You can do it by hand, just with a small number, make sure it's correct.
Yeah. Okay. So I can print like fib 4. Let's do this. That's like a reasonable place to start, right? Just call your function and look at the output. All right. So what's going on here? Okay, so it's because that's not the right one. I'll just run fiblive.py. Okay, so let's look at the outputs. So it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. That looks to me like the Fibonacci sequence. So it's okay, right? So that kind of works. So that's, you might call that informal testing, what I just performed there. So I had some idea in mind of how this should work. And then I quote unquote tested it by just looking at the outputs, whether the outputs were as expected when I actually run this function. But the problem is that this is very finicky and very brittle, because one thing that I want you to note is that this function is actually super duper slow. Right. So if I try to calculate the Fibonacci number for, let's say, a number as big as 25 or 30, this function is going to like kind of crash and burn. The reason is that it does a lot of recursive calls to the output of the function, and then it doesn't save the intermediate results. And as a consequence, the stack becomes very large, and so on and so forth. So it's correct, but it still has molasses, and it's not a very good algorithm. So
can you tell us a little bit what is the stack here?
Yeah. So let's think about what happens when you call like fib10, for instance, right? So when you call fib10, it calls fib9 and fib8. Okay, so let's look at what happens when you call fib9. When you call fib9, it calls fib8 and fib7. And when you call fib8, it calls fib7 and fib6, and so on and so forth, which means that there's kind of two branches that come off, right? So basically inside of the function, there's two calls, and those functions do two calls, and those functions do two calls. Now, some of them are shorter than others, but essentially the number of calls that get done is proportional to 2 to the n, with some constant that I don't know what it is right now. But 2 to the n is something that's O of 2 to the n it's not a good algorithm. It's just not the right way to do this. So we might be tempted like, hey, let's fix this function. But in fixing this function, we might have what's called a regression. So before, it was working correctly, but slow. It also dies if it was working sort of correctly, but slow. But But if we fix it, we might make it much faster, but we could actually break the function. So that's the thing that we want to avoid. So the first thing I am going to do then is I'm just going to comment this out for argument's sake, and I'm going to write the most basic version of a test that you can have. But in my mind, it's the most useful kind of test. Like if you learn only one thing today, and it's the thing that I'm about to show you here, I'm going to be satisfied. The thing I'm going to show you is called assert. So assert is a statement in Python, and it's kind of a funny statement. So we're going to assert that fib4 is equal to 5. Okay, so what did this do? So fib4, returns an integer. And we want to verify that this statement holds, right? If the statement does not hold, that means that something's wrong with our function. So we've established that the 0th Fibonacci number is 1, the 1th Fibonacci number is 1. After that, it goes 2, 3, and 5, right? So these are the things that we know. So now we're just going to verify through this programmatic statement that is indeed the case. And you're going to see this is going to be like so anticlimactic, but this was going to happen. Nothing. Absolutely nothing happens. However, let's say that we had made a mistake, right? Maybe that we had an off by 1 error. So that can happen. I'm sure that this has happened to you. Off by 1 error. Then what happens? It gives us an assertion error. Like, hey, the thing that you want it to be true is not true. There's a bug in your code. So instead of this thing, propagating itself through all your analyses, somehow you're using the Fibonacci number in your analyses, you immediately catch it, and then you can reason about your code and figure out like what's wrong with it. So I'm just going to Control Z and okay, return it to the previous state. And now what I'm going to do is I'm going to show you the usefulness of this code when the usefulness of this assert in a particular situation, which is I want to memoize the data. So the problem with this algo is that it computes the same value many times again and again. So you could boost it by introducing a memory array. Yeah, exactly. So we can use some caching to do that. So I'm going to just show you like a really, really simple version of this thing. My cache is going to be a dict. And then I am going to do to say, okay, so if n in cache, return cache n. Then I am, okay, so else, I do this. And then I'm going to cache n as equal to val. I'm going to set cache to a global. This is not very good code in the sense that I'm using a global, which is a thing that I said in the previous section. Don't use globals because globals are horrible. But, cooking show magic. I'm going to clean this up later. So what this is going to do is do the thing that Arslan proposed, which is to not compute the same value many times again and again. Instead, we save the intermediate results. So for instance, if we do fib10, it's going to look up fib10. If it's already, then as a consequence, it'll do fib9 and fib8. Because it does fib9, it's going to, inside of fib9, it's going to do fib8 and fib7. So it's going to run fib8. It's going to cache the result. And then once you go up the stack and you actually run fib8 again, it's going to be like, oh, no, I've already calculated this. Here's the result. right? So that's how you get this this time saving. So now I've changed a lot of, there's a lot of moving pieces here. I've changed a lot of code. It could quite well be that this code doesn't run anymore and that it's broken. Unsupported operands types for none type and none type. That's not very good. What did I do? Oh, I know. I have to return the value. Nice. Errors are your friends. Errors are things that, and that's the whole point actually of making asserts, is to transform silent errors into loud errors. You want your code to just like come kicking and screaming every time that there's something wrong with it. That's good code. Okay, so now nothing happens. That's great. Because it does the thing that we want it to do. There's another thing that that we can do, which is test it with some large number. Print 50. Okay, so that works. It doesn't crash and burn like I said that it would. So we have fixed the problem. What I could do is to go on. There's like a math sequence website, and I could find like the 50th Fibonacci value and check it against the value that I get here to create an assert. So an assert is kind of an inline test. It's the simplest kind of test, but that's the one that I think is the most useful in everyday use, especially for scientific code. Yeah, transform silent errors into loud errors. It's a good skill to have. Okay. So there's other stuff that we can test. Another thing that we can test is whether when we do, for instance, the Fibonacci. So the Fibonacci sequence is only defined for integer numbers, so non-negative integer numbers. So what if we wanted to call the Fibonacci sequence of like the -1th Fibonacci number? That doesn't really make a whole lot of sense, right? And so what we want is for the thing to throw an error in that case. So we don't want it to give us like, I don't know, like -1,000 or something. We want it to actually throw an error. So that's something that we can actually test in our code. What happens right now when we do this? So I have my coffee cup in front of my screen, so I can't find like all my icons. So that's why I'm like moving left and right. All right. What happens when we do fib -1? Recursion error, maximum recursion depth exceeded in comparison. Yeah, so I mean, this is not great because basically what Python is telling us, like that the way that we wrote our code, it crashes in like a way that's not great because it keeps calling itself because it runs into a bad thing. What we would ideally want is for it to give us like a nicer error. So one way that we could do that, for instance, is if n is smaller than 0, raise not implemented error. That not implemented error. That's kind of a better, I think that this is, potentially a better error. Right, you can see that good errors are actually like pretty helpful. Like if I ran this, I mean, I know what the code is, so this recursion error doesn't really like faze me. But if it was somebody else's code and I was trying to run this and I got a recursion error, maximum recursion depth exceeded in comparison, I'd be like, what is happening? But if I see an error like this, like not implemented error, hey, oh, I get it. It's not defined for this. I can move on with my life. What I would like, in addition, is to verify that the function actually does throw the right the right error. So what I could do then, if I wanted to verify, this is a little bit silly, but I could verify that it shows a not implemented error here by essentially like keeping track of whether it's found an error. So this is very silly code. This is not the way that you would do it, but just for argument's sake. And then I would assert that indeed I did find an error. Right. So that's one way in which I can verify that my code throws good errors. Moritz has a really good question, which is, why not assert that n is greater or equal than 0, rather than the opposite, which is to throw an error? And I think that it kind of comes down to a part of it is style. Part of it is also, just whether you want it to be like a user error or like a developer error. That's how I would say it. If you want it to be an error for the developer, then I say like an assert is good. If you want it to be an error for the user, then probably raise is the right mechanism. But these things can get kind of blurry. Like I like to do asserts for NumPy shapes a lot, just always. Every time that I throw in a NumPy shape, I check the shape with assert, and I think it works well for my use cases. So it's the line is a little bit blurry. Okay. So now one thing that I want to point out is that it's much easier to test decoupled code, which has no side effects, than it is to test coupled code. So it kind of forces you to write this modularly coupled code, which is what I was talking about earlier. Now, how can you decide what to test? If something caused a bug, you should test it, because the odds are that if something like caused you a problem in the past, it will cause you a problem again in the future. So 70% of bugs are just like old bugs that keep reappearing for whatever reason. And if you manually checked if a procedure X yielded like good, reasonable results, like we just did with FID, you write a test for it. So just these two heuristics will get you a long way. There's assert, as I've previously established. You can hide code behind main. So if _ name is equal to main, then that code will only be run if you're importing it as a script. If you're doing like Python, run this code, and if that Python file is actually meant to be used as a library, then when you're running it directly, you're running the test suite. That's a little bit. I mean, it's a good stopgap, but the next step after this is to write like a legitimate test suite. So before we really dive, I think, into deeper things, I'm going to look at let's look at the polls. Your code spaghetti, no. All right, so we have some VS Code likers. How about these questions? Okay, TDD. Okay, I think that these questions are a little bit stale. Maybe you can write them as answered, and if like people want to come back to them, they can put more functions. What do you think, Alex?
What was that about the questions?
Could you like mark them as answered? Because some of them are quite a bit stale. And then if I didn't actually answer your question already, just post it again, and I will answer it.
Okay, we'll do.
Okay, so like I said, you can use asserts. I really like to use asserts for inline tests, like checking whether the shape of a matrix is correct after a permute operation. That's like is the bane of my existence. I use this in NumPy. I use this in PyTorch. It's it often happens that like matrix operations are very tricky and like they don't really work the way that that you think they do. So just checking that the shape is correct. It's a good idea. We can hide behind if __ name is equal to main. So how we would do this here, to give you one example, is this main test. We can just write it like so. And then nothing happens, but the code is actually tested. So it does go through the hidden section and it runs the assert. However, if instead I import fiblive, this section actually never gets run. So that's what I was talking about earlier. It's just some quirk of the way that Python importing works. And so you'll see this pattern a lot. And then the final thing is to use a test suite. So I use unit test because that's what I learned, but people like PyTest a lot. I think like 80% of people use PyTest, and then 20% use unit tests. That's just what I learned at Google. I never bothered learning anything else. So here's what that looks like. So basically you create a scaffold that contains all your tests. So you import the unit test library. Then you create a class which derives from unit test.test case, and then you create functions which has test _ something in the name. And each of these tests will assert whether a statement is true or not. You'll notice that assert will come back here, but instead of being the assert statement, these are now assert methods of unit test.test case. And you can assert many things. So you can use assert true, assert false, assert close, assert throws an error, assert whatever you want, assert smaller than, and so on and so forth. So you can use that to create your own very separate test suite. And what's nice is that what you'll have is you'll have the main code on one side, and then you'll have the test code on the other side. And they don't like the test code can look like not great, it can look like just a lot of statements and be very entangled and kind of not great looking, but it doesn't pollute your main code, which is clean and sparkly and very nice. So in order to run this, once you have a test suite like this, you can just run test _ the test in question. So let me show you how this goes a little bit. So well, let's see here. I think that I have some tests ready to go in testfib. There you go. Great. Okay, so I created this class, which is called testfib. So the name doesn't really matter, but the important thing is that it subclasses from test case, from unit test.test case. And then basically what I had in asserts before, right, like asserting that the fourth element of fib is equal to 5, now I have it in these test cases. Right, so now I assert the 0th Fibonacci number is 1, the 2th Fibonacci number is 2, the 4th Fibonacci number is 5. I also test whether the 99th Fibonacci number is this big old number. And I even do like a functional test here, which is I test whether something is memoized. So memoization is what I showed you earlier, which is to make the code faster by storing the intermediate results inside of a little cache. That's called memoization. And one of the functional consequences of that is that if you run the same code twice, the second time should be much faster than the first one. So I test that it did actually do the memoization. So this is pretty neat. Once I try to run this, and I think it's going to run into an error, and I think I know which one. It's been a little while since I actually ran this. So no module named research code. So it's because we didn't pip install -e dot. Remember, this research code repository is actually based off of the Schablone template. And so like the Schablone template, it is actually installable using pip install -e dot. And this is why it couldn't find a module called research code. So returning to where we were before. So what it showed us, right, is this is the test suite. So it showed us dot, dot, and dot, right? So so these are the 3 tests in question. It ran these 3 tests in 0.001 seconds, so it takes no time at all to run this, and says, okay. So let me show you a counterexample, which is a bad test. So let's say I want to test that the -1th Fibonacci number is equal to -1,000. Okay, so this is a bogus test. Obviously, like our code won't ever tell us that. So therefore, it should highlight an error. So what's going to happen when we run this? So you see this report. We had 4 tests. The first one has the F highlighted here, this big F, and it tells us that this has failed. And the problem is this assertion error, which is that 1, which is apparently the output of this other code that I had, is not equal to -1,000, right? So now we have this big report, and it tells us that we have a failure. And so that code, very easily identifies stuff that's wrong with our code and yells loudly and tells us, no, it's wrong. So I'm just going to remove this test and answer a few questions. Okay. So if you take a TDD approach, how would you change the way you lay out your code or your files, if at all? That's a very good question. So the way that I did this presentation is I did a lot of foreshadowing, so that the way that I said that you should organize stuff in the first lesson, and the way that I said you should write your code into like functional modular code in section 2 feed naturally into section 3. So if you did these 2 first steps in your code, then your code should be a lot easier to test. But I have some further material to talk about the trickier aspects of this.
Hey, Patrick, can you tell us what is a TDD approach?
Oh, yeah, I apologize. So TDD means test-driven development. What would be an example of a statistical text not being appropriate for a data set that potentially gives us weird results? So this is what I was telling you earlier, that sometimes it's hard to tell whether your results don't fit with your intuitions because you did something wrong in the statistical testing, or because the code is bad. So an example of this might be, for instance, your data has like a very skewed distribution, and then you run a t-test that assumes that the code is normal, right? So I mean, your p-values are going to be garbage, but it doesn't mean that the code is bad. It just means that the test is bad. And so if you have that to think about, and you have oh, did I press the right button when I was doing the analysis? And you have this unknown box from, grad student from 7 years ago that like does some magical thing and you don't totally know whether it works or not. I mean, there's just like so many things that you need to keep in your head. So that's an example. Based on my experience, which part of the chart that you showed in the intro needs more writing test function? The chart that oh yeah, the numerical code. The numerical code is always the one that's the trickiest, I think. I think that, but that being said, I have successfully tested I/O functions. So that's the part that like takes the data and then transform it into a format that's easy to use after that. So for instance, like taking a like a mat file or like a CSV file and transforming it into like some pandas file that is some pandas data frame that's of the right format. So that can be pretty fruitful under some circumstances. One thing that I did a few years ago that I tried is to use test-driven development actually to test whether the data files were correct. So my wife and I were doing a meta-analysis. If you want to test your relationship, it's a great way of doing it, by the way. Have a paper together. So the analysis was a meta-analysis of the effect of a treatment on glaucoma. And it was a meta-analysis, so all the results were extracted manually from papers, which is a very like labor-intensive and very error-prone process. And so, so I was doing the statistical analysis, and she was doing the data prep and also all the medical stuff. And so it could happen that there was that some of the results were inconsistent with each other. For instance, like that the results ended up that the variance was negative or whatever, right? Because of the before and after correlation. So what I made is a bunch of asserts in R that would take the data file and that would just check whether like all the cells were okay, whether there was no nans, whether the variances were positive and everything. And then I would send her an email with the report. And we did this back and forth several times because the errors kept popping back up because, again, it's a very error-prone process. So anytime that you have something that you're like, there's so many ways this could go wrong, write a test for it. What are some other memoization strategies that don't use globals? Very good question. If you look at the sample code that I've created, I actually use a wrapper function that uses a decorator to do so. That's some Python magic. That's pretty nice. So that's the answer. So look at the code in the repo has a different way of doing it. Why do you add code in VS Code and then run the script and check the output in the terminal? You can totally do it. It's just yeah, here it is. So I think it's gonna show it. Right. So select the interpreter and then I can terminal. Python. Create terminal. Ah, there it is. Yeah. See, my terminal's right here. It's just that because right now everything is so big, it's kind of hard to have this split screen view. But yeah, I mean, I do that as well, and I use like all the built-in functions inside of VS Code. Yes, you don't have to use a separate terminal. Okay, so we have about 7 minutes left. So I think this is we're doing pretty great actually on time. So, okay, hierarchy of tests. It can be one with a runner. Yeah, so I think the ones that are the most, the two kinds of tests that you want to hit are things like asserts, which I just showed you, and unit tests. So where you test one function, which is like one unit, which we just saw. There's other kinds, but I feel like in your day-to-day workflows, you're less likely to encounter them. So what I would recommend to you is that you write lots and lots of tiny unit tests that run very quickly. So each unit test shouldn't take much more than a millisecond. Although I've written unit tests that take like several minutes to run, but it's just you want to be able to run these tests constantly, to make sure that you don't have any regressions. And with regards to your working memory, if your test suite takes more than 5 seconds to run, you will be tempted to go do something else. And by go do something else, I mean look at Twitter. I've recently did this thing where I added Twitter to my etc/host so that basically it would just show a blank page. It's helped my productivity incredibly. So it's just something to consider. It's just so tempting, 5 seconds, you're like, I don't want to waste this time. And then you completely forget what you were working on in the first place. So what do you think is the right ratio of test code to real code in the real code base?
Did you freeze, Patrick? You did? Oh, you're there.
No, I'm still here. No, I'm kidding.
Yeah, what is the ratio? I don't know, very little.
So it really depends, but what I've heard is 1 to 1 to 3 to 1. So you should have about the same amount of test code as you have real code, or maybe a little bit more test code. But if you're doing something that's very, very sensitive, I've heard someone claim that in aviation they do 100 tests, 100 lines of tests to 1 line of real code. So basically there's the thing, and then there's the thing that watches the thing, and the thing that watches the thing is much larger than the actual original thing. So yeah, I mean, it depends on the what matters to you. But it's good that they do this in aviation, because you don't want it to be brittle and be like, oops, I forgot to pip install this dependency, and then the plane goes down.
But I guess Patrick, a question I think I always had when not writing unit tests is for research code, it's mostly for you, and I guess some of it might be for public.
Mm-hmm.
And it's not really production code that you are in a company. And so I guess that's a struggle in terms of how much time should I dedicate to these sort of tests versus just keep coding what I need to do for my research.
Yeah, so I think that what I like to do is do kind of a step-by-step process, right? So I'll write the real code, and then I'll realize that the fact that the code is not written in a nice way is slowing me down. And then I'll say in the same way that I clean my apartment is once I see all the clothes lying on the floor and it getting in my way of having a nice time in the apartment, that's when I decide to clean up. And it's kind of the same way when I write code. If I run into a bug that I know for a fact, if I'd written the code in a more test-driven way, I wouldn't run into the same kind of issues. That's when I stop, and then I do a round of refactoring. So I like to do that on weekends, because it's very low pressure. And so you do the productive code on the week, and then eventually you're like, you know what, I didn't really like what I did there, so I'm going to refactor the entire thing. I'm going to write tests. And so yeah, I try to do a kind of a context switch there, but I try to use a very progressive approach. Is it actually research if it's not shareable? That's a really good question. So I think that some people are definitely going towards that end of the spectrum where they're like, well, if you can't run the code after a certain while, then if you can't figure out what was actually done in the figures to generate the figure, then it's not the kind of research that will propagate itself through time, because you can't really verify and build upon it. There's a much stronger culture in CS and machine learning conferences, for instance, to share your code. So I think we're going to cut it here. Before we go any further, I do want to, to follow. If you want to follow at home, like what we did with this CKA and what we did in terms of unit tests to actually test the CKA, please take a look at the tests, which have already been written and are in the GitHub repository. Ideally, I'd be able to live code this, but it's never happened before, so I hope I never have to. What did I want to say about this? So what I want you to do is, for your 5-minute assignment for this lesson, is to find a commented out print statement in your code and replace it with an assert. If you can just do that, and you do that like once a day for a whole week, I mean, it will change the way that you write code. Like once that switch has flipped in your mind, you'll never go back to the original way that you were doing things. I have 2 more lessons there that you can read at your own leisure, if you want. And I think that this is all the time that we have. So I thank you for being a really excellent audience, a lot of audience participation, which was awesome. And there's tons and tons of great questions that will cause me to write a lot of blog posts about in the near future. Please do the 5-minute assignments. Easy way to up your game in terms of Python, and follow me on Twitter if you want more information about this. And for those that maybe are watching the recorded session, we do have another live session at 7 p.m. And thank you, Alex. That was awesome.
All right. Well, let's thank Patrick, and thank you all for being here. As Patrick said, there's another session in the afternoon, basically covering the same